Hello, everyone. So first of all, I would like to thank our organizers and also my mentee, Eliz, for her dedication, her hard working, and her energy. So Eliz is a fourth-year undergrad student in Galatasaray University, and she will tell us about Galois representation associated to elliptic curve today.
Okay, thank you, Eliz. Let me share the screen. And let's hide things. Screen.
Sesim geliyor mu? Emin miyiz? First of all, I would like to thank everyone who made this event happen. And I can't thank to my teacher Ilkiz enough for being motivating and patience and even being perfect mentor to me. And we start by looking elliptic curves given by explicit polynomial equations called Weierstrass equation. And considering the importance of the Galois theory in number theory and the geometry, it is natural to study their representation. And furthermore, a Galois group acts naturally on algebraic varieties, which is built from polynomials and fields. And this action allows that Galois representation are viewed as automorphism groups of certain geometric objects. Okay, and this action allows that Galois representation are viewed as the automorphism group of certain geometric objects, which gives us a powerful link between the class field theory and the geometry of algebraic objects. And first of all, what is an elliptic curve? An elliptic curve that has also naturally a group structure, and we will construct this group structure by using geometry. And you can see elliptic curves in many fields, from number theory to complex analysis, even from cryptography to mathematical physics. And we will study curves given by such Weierstrass equations by using non-homogeneous coordinates of this form. And by nice, I mean that smooth projective algebraic curves of genus 1. And note that not every smooth projective algebraic curves genus 1 corresponds to an elliptic curve. It needs to have at least one rational point. And please do not forget that there is the extra point O, which have the coordinates 0, 1, 0. And we call that point at infinity. And if the coefficients of if coefficients are in the field K, then we say that the curve is defined by over the K. And if the characteristic of the field different from 2 and 3, then our Weierstrass equation is particularly simple kind like this. And the set of points of an elliptic curve forms an abelian group, and we will construct this form geometrically. Let's take an elliptic curve like this, and note that every vertical line in projective space goes through by the point at infinity. So when we take 2 points, suppose P and Q are on the elliptic curve, and if P equals, and we take the line through by P and Q, and if P equals to Q, our line will be the tangent to our curve. And of course, we know that elliptic curve has a cubic equation, so there will be a third point of intersection. Let's call this point R, this one in this case. And let this line will be the line through by R and point at infinity. And we know that this will be always the vertical line. And the third point of intersection of line with curve we called P plus Q. And note that we can compute P plus Q by using algebraic operations, and it can be computed on over any field, but we are not interested in the algebraic part. And let's examine some features of the structure we built on the last slide. First of all, if 3 points are collinear, which means that they are on the same line, their sum will be point at infinity. And we have an identity element, which is point at infinity. And you know, from the basic geometry, line through by P and Q is always equal to line through by Q and P. So by using this, our third point of intersection will be the same in both sides. So this gives us P plus Q equals to Q plus P. And when we take a point on the elliptic curve, there will be a point on the curve such that P plus that point equal to point at infinity, and we denote that point minus P. And we have an associativity law, which is not trivial, but you can find geometric or algebraic proof in our references. And you know, these properties make the elliptic curve into an abelian group. Sorry. And we gave definitions and some properties of elliptic curve. And you know, in mathematics, after examining some properties of the certain objects, we also examine maps between those objects. So because of that, I want to talk about isogenies. And we can say that isogenies are basically maps between elliptic curve, and these morphisms send identity and to identity like this. And since elliptic curve gives us a group structure, then when we add 2 points, the result we find will be on the elliptic curve too. And moreover, if we add a point on the curve with itself like n times, we get a point on the curve again. So the multiplication by n map gives us a isogeny between curve with itself like this. And the n-torsion subgroup of curve, denoted Cn, is the set of points of order n. And please realize that Cn is basically the kernel of the multiplication by n map. And the torsion subgroup of C is just defined by, we take all the union of Cn. And as an abstract group, Cn is the direct sum of two cyclic groups of order n. I will give a sketch of this, sketch of the proof. And we will use the fact that when we define curve over complex numbers is isomorphic as a group, complex numbers over this lattice. And note that when we take a point in this quotient, like say Z, is in Cn if and only if nz is in this lattice. So this gives an explicit isomorphism. Why this is an isomorphism? When we look at this map, the injectivity comes from the properties of z quotients nz, and we have the surjectivity because of the observation I just said in here. And I want to explain a little bit about extension field and Galois group. For additional background, you can look in a basic algebra text. And if K is a field containing in the subfield F, then K is said to be an extension field of F. And for an example, we can say that complex number is extension field of real numbers. And the degree of field extension is the dimension of K as a vector space over F. And when we take real numbers, I already say that complex number is extension field of real numbers, and the degree of this extension will be 2. because complex numbers form a two-dimensional real vector space. And when we take a finite extension, then K is said to be Galois over F, and the extension is Galois extension if the cardinality of automorphism group of K over F will be equal to this degree. And if the extension is Galois, and the group of automorphism K over F is called Galois group. And note that automorphism of K over F is automorphism of K, which fixes the elements of F. And equivalently, we can say that Galois extension is an algebraic field extension that is normal and separable. And before talking about this theorem, we talk about the elliptic curves, we talk about the Galois group. Now I want to combine these two together. And let C be an elliptic curve defined over a field. Then the absolute Galois group acts naturally on automorphism of elliptic curve, which is defined by the following map. Then we will show that rho n is a group homomorphism, and we call such homomorphism Galois representation. For the proof, let's take an sigma in our Galois group and take a point in our Cn. We can easily see that sigma p is in Cn. So, and the action of sigma preserves the defining equation of curve. So it gives a map from Cn to itself. And thus, each sigma induces a permutation of Cn, but this permutation is not completely arbitrary. Sigma has to satisfy the addition and the other properties. To put it differently, we can see Cn as an abelian group. Then for each sigma in the Galois group, this sigma gives a group homomorphism from Cn to itself. And we know that sigma has inverse, so we can say that sigma gives a group isomorphism from Cn to itself. And recall that we prove Cn is isomorphic to direct sum of two cyclic groups of order n. So then we say that by using basic linear algebra, Cn is generated by two elements. And we fix that elements, say P1 and P2. And we can describe all the elements like linear combination of P1 and P2. Now, take any homomorphism H, which is associated to an sigma, then for all P in Cn, we can write P like linear combination of P1 and P2. And by the homomorphism structure, we can write HP like this and again and again. So H is completely determined by the once we know the values of HP1 and HP2. Since H is a homomorphism from Cn to itself, HP1 is again in the Cn. So we can write again HP1 and HP2 like linear combination of P1 and P2, and we write this. And we can write this equation by using matrix form. And if we take another homomorphism like H, we call the G homomorphism, then we can compose these two homomorphisms like with matrix multiplication. And you know, if we take G equals to inverse of H, this multiplication will be the identity matrix. So so then the homomorphism we studied previous slides are actually isomorphism because they have inverses. Thus, the matrix associated to an isomorphism is invertible, and conversely, we can use any invertible matrix for define an isomorphism of Cn to itself. So I think we should look at the invertible square matrices, which we say general linear group, but in our cases, this group will be GL2 because we had two equations like this. And for the summarize, we took an element in the Galois group. So we have an associative automorphism of Cn. And for each automorphism, we have an associative matrix in GL2. So we have the following map. And we calculate the matrix multiplication. So this shows that this is equal to this. So this equation gives us rho is a group homomorphism. And when we consider the Galois group of this, the rho n we built earlier is not just a homomorphism, is just one-to-one group homomorphism. And before talking about the proof, I want to define the elements of this field. And we know Cn is the points of order n, and we can write the elements of Cn like this. And we just build a field generated over rational numbers by x and y coordinates. We just take all of this and we take the extension field of Q, and this is, of course, will be the finite extension. And for the proof, we already know that it is a homomorphism. So it is sufficient to show that kernel is trivial for the one-to-one. And we take a point in the Galois group. And if it is in the kernel, so we know that this must be equal to this, the identity matrix. So we know the representation from the representation, this must be equal to this. So this means that sigma P1 equals to P1 and sigma P2 equals to P2. So sigma is fixed our basis element, right? So it fixed all the elements of Cn. And by the definition, we have the sigma xy equals to sigma x comma sigma y. Hence, sigma fixed the generators of the field. This means that sigma is the identity element of Galois group, and which proves that the kernel of rho n consists only the identity element. Therefore, rho n is one-to-one. And let's look at really basic example. Let's take this elliptic curve over Q. We have C2, and we know that QC2 defined like we take all the coordinates. So we take 0, 0, I, 0, minus I, 0. So it is just equal to field of generated by I, Qi. And the Galois group will be this one. The sigma 0 is the identity, and the sigma 1 will be the complex conjugate. So to describe the representation, we fix our basis elements like we did before. We fix P1 like this and P2 like this. So since the sigma is the complex conjugate, sigma 1 is the complex conjugate of 0, 0 will be equal to this. And the complex conjugate of I0, I, 0 will be the minus I, 0 will be equal to this. So the associated matrix to sigma 1 will be this. So we have the representation here. And notice that if we had used different bases, then the value of the representation will be the different matrix. And note that Galois representation associated to an elliptic curve need not to be isomorphism. We construct a field extension with Galois group, and we prove that rho n is a homomorphism, and in some cases rho n is a one-to-one homomorphism. But notice that rho n need not to be onto. So it turns out that for most elliptic curve and for most values of n, the representation rho n are almost onto. before the talking about what I mean the almost onto, I want to give a definition. If the endomorphism of curve is strictly larger than Z, then we say that curve has a complex multiplication. And I want to quote a beautiful and difficult theorem of Jean-Pierre Serre that explains in some sense what it means to say that rho n are almost onto. When we take an elliptic curve over a number field K without complex multiplication, the index of the image rho n in automorphism group of n-torsion subgroup is bounded by a constant depending on the curve and depending on the field. Thank you for listening.